to start out here, I want to introduce our look at applications with a little bit of a history here. The study of calculus was actually developed by two men. And this is one of the amazing things you see happen over and over again throughout the history of mathematics. You'll see people in different parts of the world developing the same ideas. You know, for example, with a lot of the geometry. A lot of the geometry we look at, we see it as, you know, Euclid's Elements, or Pythagoras, you know, the Greeks that really dominated the study of geometry at the time. But the fact of the matter is that there was a lot of exploration and stuff going on at kind of the same time in history over in India and in China. There were other people discovering some of the same things that the Greeks were discovering, okay? In fact, the word algebra is actually part of a man's name. He was, where was he from? Turkey, I think. But part of his name was Al-Jaber. Khwarizmi, I think, was his last name.
Why do we call it Khwarizmi?
Because that's worse than algebra to try to say. But actually, the word algebra also means something else. I forget. But he actually wrote a book, you know, laying out a lot of the algebra principles and things that we use today, even. But Sir Isaac Newton we're familiar with, but another mathematician, Gottfried Wilhelm von Leibniz. Okay, he was a German mathematician. They actually came up with a lot of the principles of calculus, the derivative and integral, at about the same time. Okay, this is what's kind of interesting. This was before the days of copyright and all that kind of thing. Newton, history would tell us, actually figured out a lot of this stuff about 20 or 30 years before Leibniz did. Okay? The problem was that Newton was a bit of a perfectionist, and he was a little bit more, you know, not secretive, but he kept things a little more to himself. So he actually didn't publish his findings. Okay?
So,
well, in his notes and things like that, and in people he talked to, he would talk to people about it and stuff. But he never actually published his work. Leibniz figured out a lot of the same stuff, but he figured it out about 20 or 30 years later, but he published it right away. And once he published it, Newton was like, oh yeah, I've been doing that for years. You know, so there's like this debate among geeks, you know, who invented calculus or who discovered calculus. And really we could give both the men credit because they both discovered it, even though one did it before, the other one published it before, you know, so we can give both of them credit here. And who knows, there might have been a mathematician over in the Far East or something who had discovered the same stuff. So that's what's cool about math. As you look at the history, there's a lot of people discovering a lot of the same things around the same times. Okay, now what led them to these discoveries was actually the growing field of optics at the time. You had people building telescopes and things like that to try to examine the stars and examine other planets and things. And some of these were very crude, some of them were a little more sophisticated, but optics is really the study of using lenses and mirrors and things. So you had people trying to build better telescopes, you had people trying to build microscopes, you know, how to look at tiny things. And also you had people starting to make glasses and stuff like that. Like Ben Franklin. These guys lived, I believe, in the late 16th century or 17th century. I forget. But then you had like Ben Franklin inventing the bifocals. Glasses had been around for a while at that point. But optics was, really, as you can see in this bottom diagram here, we're looking at how light comes into our eye and understanding the lenses involved, the lens of our eyeball, and what would happen if we put another lens in front of our eyeball. How is that going to impact how the light comes in? If we bounce it off of something else, what's going to happen? And being able to predict that kind of thing was kind of what they were trying to do, all right? And it all actually goes back to this idea of reflection. You have what's called the normal line. So you have this mirror, and in this diagram here it's flat, but the normal is perpendicular to that surface. And if I reflect something, the angle of incidence, that's this angle right here, the angle away from the normal that something is coming into the mirror, will equal the angle of reflection. So this angle right here is going to be equal. All right? So in order to predict what light is going to do if we bounce it off of something, we've got to be able to figure out what this angle is. Okay? Well, that's not too hard when we have a flat surface, but when we have a curve like this, that's where it gets complicated. And that's where they started looking at derivatives and trying to figure out, okay, this is a curve, but at this exact moment, what is the slope of my tangent line? What angle is that surface at that one moment? And the reason why we measure from a normal line is because since it is curved, okay, here's a normal. Since it's curved, we can't really find an angle from that curved surface. So we have this normal line, and we can then measure, all right, what's this angle right there? There's our angle of incidence. And then it's going to equal the angle of reflection on the other side. Okay? That then allows us to predict things like, okay, when I am looking at this curved surface, and a curved surface like this that makes something look bigger, all right, where should I place the thing I'm looking at in order to see it clearly? See it in focus. In fact, what you're doing when you're adjusting a microscope, with that fine tuning, is you're making really tiny adjustments to how far away the mirror is from, or the lenses are from what you're looking at, so that the focus is exactly where it needs to be for you to see it clearly. Okay? So you have all of these reflections, but to predict that, you've got to know the angles. And to know the angles, you need the normal line. And to know the normal line, you have to know the tangent line. So the tangent line was really just kind of a necessary step in the process of finding what they really wanted to find, which was the normal. Okay? So it's kind of an interesting study of the history there. And now those principles behind optics are now being used for radio and satellite waves, for lasers, all kinds of different things. Okay? So it's gone way beyond just bouncing light and being able to see clearly. Okay? Yeah?
Is it okay if I fill my water and use the bathroom?
Now, let's talk about a little bit of quick review here. We're going to look at these two examples in like 3 different contexts. Alright? So, the first one here, I want to make sure we understand and have down the thing that we have done in the past, and that is finding the equation of a tangent line. Okay? So, you'll notice in the diagram up here we have this curve, y equals f of x. Here's our point of tangency. Now, they use a little different term at this point. They use a point of contact. And the only reason they use point of contact instead of tangency is because we are also talking about the normal. So, it's the point where the tangent line and the normal line will contact our function, okay? But for right now, let's look at the tangent line. And if you remember back to Algebra 1, when you learned how to find equations of lines, you got to know two things to find the equation of a line: slope and a point. The point is going to be that point of contact. The slope we're going to get from the derivative. Okay? So, let's work our way through these two here and find the equation of the tangent to, in this case, y equals x minus 2x squared plus 3 at the point where x equals 2. Okay? Now, what point is that we're looking at if x is 2? What's our point of contact going to be?
2, 0.
How do you get 0?
I don't really know.
Wait, is it gonna be
Okay.
negative
Where you get negative 3?
You plug it into.
Plug it in, okay? Plug it into the function, okay? So if you plug in 2 minus 8 plus 3, we get negative 3, okay? That, by the way, guys, is one of the more common mistakes we will make. We'll accidentally plug that 2 into something else. Anytime you're looking for a point on the curve, make sure you plug that value of x back into the curve itself. Okay? So now we have a point. All we need now is the slope. So, like we said before, we're going to do dy dx. And the derivative of this function is?
1 minus 4x.
Good, 1 minus 4x. So, our slope is going to be that when x equals 2. So 1 minus 8 is negative 7. Once you have that, really, I don't care how you get the equation of the line. Alright, you guys have been finding equations of lines for years, so you should know how to do that, but some of you might like using slope-intercept forms, some of you might like using point-slope forms, some of you might just do it logically. I don't care, okay, as long as you can just get the equation of the line. So, if I used point-slope form, I'd have y minus a negative 3 equals the slope times x minus 2, and I would get y equals a negative 7x plus 14 minus 3 is a plus 11. Okay? So that is the equation of our tangent line. Okay? So by the way, I know this parabola is going to have, let's see, I think a max point somewhere around here. That's what this is going to look like. It's kind of ugly. But here's our point that we're looking at, that point 2, negative 3. And the line that we just found is, you know, it's crossing up here at 11 and it has a slope of negative 7. Okay, so there's the line that we just found. Okay. Now, any questions about that? Got it? Alright, take a couple minutes and try B on your own. Okay? Same process, try B on your own. Alright, so if you plug in 4, you get to 0.43. That's what we're looking for. What's the derivative of our function here?
1/2 x the negative 1/2 y.
Alright, yeah, 1/2 x to negative 1/2, which is 1 over 2 root x, if you simplify that. Okay? So, when x is 4, what's my slope?
1 over 4.
Yeah, 1 over 2 times the square root of 4 is 1 over 2 times 2, which is 1/4. So I plug that in with my point, and I can get the equation of my line. Y equals 1/4 x. Let's see, that'd be a minus 1 plus 3, so that'd be plus 2. Okay? So there's our tangent line. Okay? Now, for our normal, remember we said, what relationship did the normal have to the tangent line? It's perpendicular. And you guys know, back from Algebra 1, that perpendicular lines have slopes that are opposite reciprocals. Okay? So, what I'm showing you here shouldn't be a huge surprise. We have the gradient, or the slope of the normal to the curve, is negative 1 over the derivative. Okay, the derivative is the slope of the tangent. If we want perpendicular to that, we got to do negative 1 over the slope of the tangent. Okay, now notice here for notation, this is helpful in distinguishing in our minds what's going on here. Notice they do m with a little subscript of n. That's the slope of the normal. Okay, that will help you keep straight what's what as you're doing different problems and things. Okay, so we've got these same functions. On the first one here, we had that point 2. It was 2 negative 3, right? 2 minus 8 plus 3. Yeah, that was our point. But the slope that we found, because dy dx is 1 minus 4x, the slope was negative 7. So what would the slope of the normal line be?
1/7.
Yeah, positive 1/7. Okay. That's really the only difference between what we just did and what we're trying to find now.
So we plug in negative 7 into f prime of a.
We plug in 2. X is 2. Okay. Oh, wait. I'm sorry. Yes. Up there. The f prime of a.
Yeah.
Yeah, that in this case would be negative 7. So negative 1 over negative 7 would be a positive 1/7.
Okay.
Yes.
So we have to do all the steps we did previously, but just do the one extra step that we did.
Exactly, yeah. For this one, if we were just asked to find the normal line at the first place, we would have done everything that we did to get the slope, but now we're going to use the 1/7. But the rest of this is essentially the same. Y minus a negative 3 equals 1/7 times x minus 2. All we're doing is we're putting a different slope in. Same point still, but different slope. So y would equal 1/7 x minus 3 2/7, if you simplify that. Okay? We're using that point slope form. Point slope form says y minus y1 equals m times x minus x1. That's to find the equation of a line. Now on this other one, we already had the point was 4, 3. What was the slope of the tangent that we had gotten?
1/4.
1/4. So the slope of the normal would equal negative 4. Okay? Be negative 4. And now again, same process. Y equals, or I'm sorry, not equals, y minus 3 equals the slope times x minus 4. We get y equals a negative 4x. You have plus 16, and you have to add the 3, so it would be a plus 19. Okay. Does that make sense? Okay. So not terribly difficult once you know what you're looking for. Okay. So let's take one more step here. Horizontal tangents. Okay, horizontal tangents. I'll put this in like we had before. Dy dx is 1 minus 4x. Over here, dy dx is 1 over 2 root x. Okay, horizontal tangents are going to be significant because what did we say? We know horizontal lines have a slope equal to 0. All right? We've known that a long time. That means our derivative would equal 0. What did we say was the significance of these? When our slope is 0, what does that indicate? Yes. Okay, it's going to be a max or min point typically, and we're going to look at that more closely this unit and kind of clarify and expand on that idea. But typically it's going to give us a max or min point. So these are significant things here. All right, but what we have to do here is we need to find where the derivative equals 0. That's going to tell us where that point would be, okay? So in this case here, I can set this equal to 0, and I get x equal to 1/4. Okay? Now that's where on the graph my slope equals 0. Which actually, since you know this is a parabola, we said it looks something like this. That horizontal tangent here is going to be right there at 1/4. The question, though, is what actually is the horizontal tangent? How do I figure out what that line is? Because I know it's got to be y equals some number to be a horizontal line. So what do I do with the 1/4?
You plug it into the equation.
Plug it in. Where am I going to plug it in?
Into the original.
Into the original, okay? If I plug it in the derivative, what am I going to get? 0, because that's where it came from, okay? Now, it's not that you can't get 0 when you plug it in the original function, but okay, you'll definitely get 0 if you plug it in the derivative, and that won't give us a point on our function. So if I plug in 1/4, I get 1/4 minus 2 times 1/4 squared. That's a minus 1/8 plus 3. So 1/4 minus 1/8 plus 3 is 3 1/8. So that's my horizontal tangent. Y equals 3 1/8. Okay?
You said it's horizontal tangent?
Yes. Now let's think about B in this case as well. When will this equal 0? It won't. Okay? This is no solution here. So there are no horizontal tangents. And if you think about the original graph, it makes sense here. Look at our original graph. The radical function typically starts at 0, 0. This one shifted up 1 unit, okay? So check this out. It looks like this. Does that graph ever have a max or a min point? No. Okay? It continues to increase forever. So it makes sense that our slope is never going to be equal to 0. Okay? All right, so that's a few those are a few applications there of our derivative to start with. Okay? Now, another thing that we want to do is we want to apply this to some functions that maybe we're not as familiar working with. Okay? I don't want us to forget those other rules. Okay, and also the few times we did find equations of tangent lines earlier, we were just dealing with polynomials, okay? Here we have a logarithmic function, okay? Now, think with me here. Our logarithmic function, if you remember your parent function, it hits the point 1, 0, because anything to the 0 power is 1, all right? And it's going to look like this. And it has an asymptote here as it approaches the y-axis. Okay? Now, we want to show that the equation of the tangent line at the point where y equals 1, so y equals -1, so we'll say it's right there, is y equals ex minus 2. In other words, here's our tangent line. We want to show whether or not this is y equals ex minus 2. Put a big question mark there, because that's what we're trying to determine. Okay? So before we, as we go to tackle this, we're going to do the same things we did before. We need to find the point of contact, or the point of tangency. So how am I going to figure that out?
Find derivative.
Not yet. I just need a point of contact at this point.
Plug it in.
What does that mean?
Plug in what? Plug in -1 for
For the y.
y. So it's -1 equals ln of x. Okay? I'm trying to find this point right here. I know it's something -1. That's what we're told. Okay?
Why is it like X?
That's the function we were given.
Oh.
Now, how do I solve for x here? Okay? If I raise both things to a power of e, or not to the power of e, if I put both of those as e to that power, e to the ln of x, e and ln undo each other, so I have just x, and I have e to the -1, which is 1 over e. Okay? Do not put this in as a decimal, just leave it as 1 over e. But that's the point that we're going to use.
Now we can
Now we'll find the derivative, because we got to get the slope. Okay? So, what's the derivative of natural log of x? 1 over x. Good, we remember from yesterday. Okay, 1 over x. So, if I want the slope, I've got to plug in the value of x at the point that we're trying to find the slope at. So that's 1 over e, which is just e. Well, now I at least know that my slope is correct. I know it's y equals ex something, and actually just looking at it, I know it's y equals ex minus something. It's got to be negative somewhere down there. So now I just have to prove that it's a minus 2. So I get my equation y minus the negative 1 equals e times x minus the x coordinate 1 over e. Alright, and again, we just simplify y plus 1 equals ex minus what? If I'm distributing, minus 1. So now I subtract another 1 to solve for y, and y equals ex minus 2. And we are there. Okay? One side note. Anytime you're told to show, you had a couple of these on the test, you're going to see ones like this on the exam, okay? Anytime you're told to show, make sure you show extra, maybe even more steps than you would typically show in showing your work, okay? When I read the mark schemes for these types of problems, it'll have it set up like the first steps, and then it says, working clearly progresses to whatever. Now that clearly progresses is kind of subjective. So we don't want to leave any doubt in the reader's mind that we know what we're doing. So that's why it's worth it. Just show all your work. You know, that's why I would go ahead and show distributing the e and then solving for y. Okay, just to make sure. All right, any questions? Okay.